go, introduce yourself, get the ball across the plate. You got 20 minutes.
Okay, let's see. Does sharing my screen work?
Yes, fine, perfect.
Awesome. Okay, so my name is Philip Zembrod, and this is a bit of work from my retro kitchen again. Something that I presented at last year's Eurofourth, but I had for a while intended to present it to this audience as well. And when I saw the call for speaker still up yesterday, that triggered me, as Kevin mentioned. So the motivation for this, so this is a small profiler that I built for 16-bit indirected threaded FoxForth, on which I had written mostly way back in my university days, and at the beginning of the pandemic had finished it, a small C compiler. And basically I was pretty happy with it, only it was very small, very slow. And I felt slower than it needed to be. Obvious fix for that is, of course, to optimize hotspots, only I didn't know where they were. So the question I wanted to answer is, where does my compiler spend its time? I was looking for a profiler that could work at different levels. So I was both interested in sort of where on the large module scale is the actual time spent, how much is spent in the parser, how much in the scanner, in the code generator, but also the ability to drill down into smaller granularity all the way down to word levels. And ideally, I would like to have that self-hosted, well, because I did some research on prior art. I found some code that could time individual words. I could let next log out all timestamps, but then I would have to, well, post-process that. Clearly, if I had a C-written virtual machine, that would be great. That could be instrumented. But in the end, all that I found was things, well, nothing that really fit the problem, things that could tell me how fast is a certain word, but not really the sort of overview question, where is the time spent? And that's, of course, a happy situation if you have the excuse to build something new. And I thought mostly around what could I do with the next routine, and that's what the whole thing really hinges on. That's why I point out it's for ITC. The same concept would work for DTC, for direct threaded as well. For subroutine threaded, I don't think so. So with next, I could count how often a word was invoked. I could count how many next cycles I have within a word, sort of IP fetches between the colon and the semicolon. I could count those cycles and at the same time sum up the time spent in that word. I could do the same thing for a range of words. So if I'm interested in let's say the scanner, I could count cycles and time that's spent within the scanner. And I could split my entire code into these kind of code ranges, memory ranges. I call them buckets, and then sum stuff up per bucket. And the idea then was, okay, if I have that for a high-level overview, I could split a bucket in sub-buckets and then sort of drill down to the level of detail that I need. And at that point, I was starting to get confident, okay, this is actually something that could work. The prerequisite, of course, was that this instrument and that I went for only single interval buckets, only 8 buckets, so that I could do a quick 3-compare binary search in an unrolled loop. And that should be reasonably fast, I figured. A few more questions. What about time spent in the fourth kernel? And I decided, well, that is really time that should be added to the account, basically to the bucket that called into the kernel. What about non-core code outside of buckets? So basically the rest of the application, but not in one of the buckets that I'm interested in at the moment. And I defined a default sort of rest bucket 0, where everything else of the runtime cycles and times goes into. And for time measurement, I was able to use the two 16-bit timers of the 6526 interface adapter, which can run at CPU clock. So there I had a 32-bit timer, which gave enough range and enough resolution for the purpose that I had, or so it turned out. And this is now the actual code of the next routine. This find bucket here, essentially what you're seeing here, this is the 3 compare IPs under each other is the rolled out 3 compare binary search. The top here, current bucket, this is the check, are we in the fourth kernel? So then the bucket to find is the current bucket. Each bucket has a beginning at the end. After the binary search, you have a candidate for the lower end, for the lower limit of the bucket. Then you check, are we still underneath the corresponding high limit? If yes, we've got the right bucket. Otherwise, we're in the default bucket. And fun fact, when I read through this code again for this talk, I suspect I have one more bug in it. So I'll have to do some more digging there. So, okay. This is what then the actual next routine looks like. First of all, we disable the timer, so we don't want to measure the time that we're spending in the instrumentation. We calculate the time since the last, so calculate the last time delta. We find the current bucket, increment the count, increment the time, or add to the time of that bucket, prepare for the next time delta, and then set everything going again. And this here is the code that activates this or patches in this next routine. For instrumenting the code, I ended up with a mode or with a method to define buckets inline in the code. So they're all prefixed by this /prof word, which usually is a comment. So this is only activated when I'm running in profiling mode. And you define a bucket. This is the name, and then at some point you say here the bucket ends. And typically I have for the top level buckets have them set around one module file. In a few cases it's more than one. The alternative that I considered was to define buckets with sort of just with tick word expressions, and figured out the end of a bucket would then be somewhat less intuitive. And Volkswagen also has this nice feature of headerless words, and for those the bucket definition would then also be a bit difficult. This is what nested buckets for drilling down look like. I'll skim over this now. Here we have groups of 8 metrics, of 8 buckets grouped together in a metric. You can have several metrics compiled into the same binary, and then do measurements, just activating them interactively without recompiling, which turned out to be very handy. Yeah, this is basically an overview of what I just talked about. And a few words about the results that I got with that. So this here is the first compile run, the first instrumented run. And what I noticed, the first thing, oops, one back, is that input is the module that just reads source code. That took a suspicious long time. Turned out just printing the source code while reading it was the majority of time that went into that. So disabling list while compile already got me a 10% win, quite unexpected. And the second big one was the scanner. So the next step was then to drill down into the scanner. And here again, something unexpected stood out. The code that parsed operators turned out I had some nested, unnecessary linear searches in there. So I re-implemented the operator scanning, all without touching assembly yet. So this is all just pure forth implementation. So I got that one down by a factor of 10. And then I had this suspicious rest here. So this was just a little bit that I thought is not really interesting. And that turned out to be the second biggest bucket in the scanner. And when I drilled down into that, what I found is I had built the scanner with a next word backward mechanism. So the parser says, okay, give me the next word. I'll see if I can do something with it. No, I can't, backward, and then going to the next parser rule. And it turned out that this to and fro, because it happened so often, was the next unnecessary and big time sink. So I just changed the interface of the scanner from a to and fro to a just give me the current word, and if it matches, then I accept it. And that again gave an, well, reduced it by 80% or something like that. So just to go, well, we'll have the overview on the next. No, the page afterwards. So the last optimization I did in the scanner now, I actually did employ some assembly in the parsing of characters, so detecting alphas, and in the string search for token recognition that together lives in these two modules gave another noticeable speed up. And so what this overall gave me is from, so this is in microseconds. No, sorry. Yes, this here on top is microseconds, and the rest is next counts. So I saved on my end-to-end test suite that I had, which I used for measuring 31% time, so 45% gain of velocity. And from this point, and also looking at the overall distribution, where is the time spent? This now started to look reasonable. Time is spent where there's actual work to do. So that's when I stopped the optimizing exercise. Yeah, here are a few links where you can find the code. I'll send the slides later to the canonical place. Conclusion, this profile approach turned out to be actually pretty practical. I did get the overview that I wanted and could get a pretty good optimization with relatively little effort. And the whole profiler is just 190 lines of code. The cost for running it is about a 4-fold slowdown, a bit less. So profiler instrumented, the thing runs at a bit faster than 1/4 of the standard speed. And yeah, what the approach needs is a next routine, so ITC or DTC. For a macro, next one would probably have to patch that to actually get a subroutine. And with that, I'm through. Yay, made it.
I have a question. By the way, I comment. I love the idea of the 8 buckets and sort of curtailing the amount of resources that you use in the instrumentation so it can be fixed. Yeah, I noticed you had 9 buckets though in the prior slide. What's going on there?
Yeah, the 9th bucket is the rest.
Ah.
So I've got 8 intervals. And whatever I can't sort in any of those or associate with the 4th kernel it goes into the rest bucket.
I see. Very neat.
And incidentally, the possible bug that I have is I suspect that application code underneath the lowest bucket, but beyond the end of the 4th kernel is actually identified as 4th kernel code, but I have to revisit that, look at my tests, etc.
Cool. Thank you.
No, leave it on. So we're going to move on to Bob Armstrong. You got your 5 minutes of fame here.
Yeah, I've already said a bunch, so won't say much more. I will